be here and to see some familiar faces. I hope it's been a good school so far. I don't know if this talk is really pitched exactly at the same level topic background as the other talks have been. I get a show of hands of people who do like quantum field theory. Okay, yeah, there's somewhat of a majority of you, and then mathematicians, people who consider themselves mathematicians. Also, okay, so there must be some overlap there. Yeah, this project. I mean, some of our co-authors are here. See Cameron there. It's really sort of driven by both mathematics and quantum field theory. So I think it's a fun thing to talk about. I don't know what the direct connections are to categorical symmetries and so on, but it's some of the same flavors, lots of anomalies and things that you do with them, and kind of like there'll be some open problems, and I'll give some exercises, and besides these references, which are our papers, I'll talk about some other papers, and it'll be sort of lots of a challenge to try to generalize these things, maybe into categorical directions. Okay, so I'll tell you what are our goals roughly. So we're going to talk about symmetry breaking. And we're going to talk about a particular type of defect that occurs in symmetry when you study symmetry breaking, called the row defect subset. And this includes many familiar kinds of defects that we're interested in, such as domain walls, vortices. We want to describe gapless modes localized to these defects, and learn when to predict when these gapless modes occur or don't occur. In particular, we're going to prove some kind of defect to bulk anomaly matching, which is the kind of generalization of the bulk boundary correspondence, the usual one. Then we're going to describe non-trivial families of TQFTs and their associated family anomalies, higher dimensional generalizations of the quantum mechanical Berry phase, and use that to learn about the structure of phase diagrams. We'll add symmetries. To 3. We'll get some kind of generalized index theory associated with these families. And we'll tie it all together with the longest X sequence. So we'll see how far we get. I mean, we have 4 hours, but I encourage you to ask questions. I'll try to be pretty basic and try to be as precise as I can about what we're talking about. So let's talk about symmetry breaking. Symmetry breaking is pretty fundamental in physics, and I would roughly divide it into 3 types. You have explicit symmetry breaking, which I'll call ESV. You have spontaneous And kind of a bit distinct from these two, you can have gauge symmetry breaking, this Higgs mechanism. Now this one is mostly conceptually distinct from the other two, but it has some similarities, so we still call it symmetry breaking often. So let's see, to contrast these. So spontaneous symmetry breaking, this is when you have a global symmetry. For example, a group G maybe a finite dimensional Lie group or something like that. Then, although you have this symmetry, the ground states, but ground states are not symmetric. Typically, they just preserve, each state. There's some subgroup that stabilizes that state, and you can say that they're going to have to be multiple of them because if G doesn't fix the state, then it has to send one ground state into another. So what do I mean by this? So ground state can be interpreted extremely loosely. For example, here's an optimization problem. You have 4 dots, which are arranged at the vertices of a square, and you want to connect them by some graph that has the shortest possible total length. So this problem has all of the symmetries of the square, right? You might expect that the solutions, maybe the solution is also the symmetric one. That's actually not true. So this is not the lowest length configuration you can find. Actually, you do better to kind of bring 2 of the strands together early, and then join them. And so there are 2 distinct minimizing solutions, which we might call ground states, that are the lowest energy configuration. So these each preserve D4 subgroup D8. In this case, the symmetry acts transitively on the solution. So there's 2 solutions, and there's 2 cosets of this stabilizer. Another one, which is maybe more physics-ish, is to minimize the potential. For example, sort of double well potential. So looks like this. There's a symmetry, but the minima, here's x equals 0. There's a maximum at the symmetric point. So the minima is actually at these non-symmetric points. So here we have V2, which is broken to nothing. Okay. Contrast this with explicit symmetry breaking. So this is where we take a G symmetric system. By system, you can just mean some kind of math problem. But we want to object it to, say, order epsilon stations breaking. Breaking the symmetry. So, for example, in this double well potential problem, we could add this term that's linear in X. with a small coefficient. Well, it doesn't have to be small. I just want to keep track of it by having some kind of power series in epsilon. And that's going to raise the energy with this sign. It raises the energy of the positive minimum amount. So in nature, there's always explicit symmetry breaking. Well, except possibly for symmetries like Lorentz invariance, although certainly in the lab, all those symmetries are broken. But and that seems to kind of spoil this story about spontaneous symmetry breaking because one minimum is still selected. But as long as these perturbations are small, then you can still see the sort of effects of spontaneous symmetry breaking, like multiple ground states.
I have a question.
Yes.
So in the case of spontaneous symmetry breaking, do you still have conserved currents for G at the low energy?
So both the examples I gave were discrete. So there's not really a current.
Uh,
You always have the conserved currents. If you're thinking about quantum field theory, there's some operators in the theory.
Right.
If you have spontaneous symmetry breaking, then those are the things that create the Goldstone modes. So they're still there, but they don't preserve the ground state anymore. Now we really have spatial locality in many of the problems that we're interested in. We want to do field theory, so we want to do a problem like this where you're not just minimizing the potential that's a function of a single number, but that's a function of like another function of like a field or something like that. So for instance, you might want to minimize this energy. Now, phi is some real valued function. We have some energy density that we integrate over d-dimensional space. Well, if we just minimize this, then the minimum will still have phi be constant because this gradient squared term is positive. So phi prefers to be constant and just sit at the minimum. But interesting things happen when you either turn on some non-zero temperature, quantum fluctuations. So in this case, the constant solution will be extremely rare to sample if you're thinking about it in positive temperature. And depending on the dimension, this sort of changes the picture. So what we do in this case, so these are sort of statistical cases. So we're not exactly interested in the minimum. We're interested in the expected values of phi. So one way to measure the spontaneous symmetry breaking here is to look at connected correlation functions. So if I look at this quantity, bracket is the expectation value of that object. So let's say that we're in this kind of symmetry breaking picture where phi spends most of its time sitting in one of those minima. Well, then you might expect that far away, phi is still sitting in the same minimum. That's going to be when this is 1. But if there's a lot of fluctuations, then phi is going to sort of swap from one minimum to the other, and you won't have any order. So what this looks like, you have regions. Let's say where you're in the, let's say we're in the symmetry breaking regime. then the typical state that you're sampling will be in the positive minimum mostly everywhere, but there will be sort of islands where it's in the other minimum. But these islands will be sort of rare enough that they don't spoil this correlation function. So these boundaries between these domains, open main wall. And while they move around, they have some complicated dynamics. If you're thinking about the quantum case, or you do some kind of like thermodynamics to think about, and these move around in some complicated way. And they have energy that's roughly equal to their surface area. So there's a competition between wanting, say, positive temperature. There's a competition between wanting to minimize the energy, not having any domain walls, and the entropic favorability of having these domain walls around. So for example, in 1D, at any finite temperature, you don't get any order because, say, you're in this plus state, then very likely that you'll create a domain where you're in the minus minimum. And these have constant energy and they're free to wander around. So they're just as likely to wander this way as they are to wander in and annihilate. So you expect that the system will flip from the positive to the minus.
I'm sorry,
Yes.
could you say what temperature is in this context?
I'm being sort of vague because there's many ways to model these things. It's sort of like a general phenomenon, but you could do like a Gibbs ensemble or this energy functional or something like that. So I mean, it's a particular, what temperature means is it's a particular way of averaging over Y's functions phi, with weighting that's determined by T. So basically the relative weight of the configuration is E minus the energy over the temperature. So when the temperature is 0, you only sample the energy equals 0 states. But when the temperature is very large, then the energy is less important. These are all sort of. So I mean, like this correlation function, you measure phi here, and you measure phi here. Now, this is going to be +1 if they both lie in the positive region. It's going to be -1 if this happens to be encircled by one of these islands. So whether this correlation function is non-zero has to do with whether these islands are kind of everywhere or they're sort of confined. So this is just to motivate thinking about these domain walls as the sort of agents of this symmetry breaking. Okay. Well, there are other sorts of defects that are interesting. For instance, now we take a continuous symmetry example. So you have a U1 symmetry that is broken down to nothing. You can think about modeling this by a complex valued function potential. This. Now the argument of phi is what's interesting. And a novelty of this continuous case, you can choose phi to be the e to the ikx. 5x. And if k is small, this state, this has energy approximately k. So you have these massless Goldstone modes in this case. And these will spoil, they'll also spoil your 1D order. You don't have domain walls anymore because you can continuously vary from one vacuum to the other. So this potential has an entire circle of minima. So there's not this just two discrete minima. You can move from one to the other. We could draw that as an arrow in the plane. So what you can have is in 2D and higher, you can have these vortices. So you can have a point where phi vanishes and the argument of phi going around like this. You also have an anti-vortex. Field interpolates between these two. And depending on your system, these could be repulsive or attractive, roughly speaking. These have energy that grows logarithmic in their separation. Because if you think about an isolated vortex, that varies with theta at a rate 1 over r, because around a complete circle, it has to wind by a constant amount. Some constant over r. So this means you have an energy density. Over r squared, which if you integrate in 2D, will give you log. So these vortices actually, because of this log is not quite enough to overcome entropy. So this still boils order in 2D, but in a sort of interesting way. You get this quasi by long-range order with some non-trivial scaling behavior in this connected correlation function. Looks like 1 over x to a variable power. So that's for any temperature, any positive temperature.
Could you explain again where these vortices come from?
So I'm drawing this arrow to denote the argument of phi. But when phi is 0, there's no well-defined argument. So if you have, say, let's say complex analysis, phi is z, then at z equals 0, it looks like this, right? The argument winds around. This would look like 1 over. Sorry, this would look like, well, I forget if it's z or z bar. Anyway. Right, so these exist because this phase can vary in space, and if it happens to wind somewhere, then there has to be some kind of place inside where the field vanishes. Right, so there's a kind of topological number that's protecting these things.
Right.
Yes.
So here the symmetry U1 is a symmetry of the potential, but not the space of observables. Is that how I'm supposed to think of this?
Yeah, exactly. So this doesn't depend on the argument of phi, but if you want to minimize it, you have to choose some non-zero phi, and it has an argument. Yes.
What did you say the property of the long range order was? You said it's some power law case?
Yeah, so these have connected correlation functions. It's like this. One over x to some power. So it's not exactly ordered in the sense that, so you really have symmetry breaking when this has a non-zero limit as x gets very far away from zero. So x to infinity, that should have some non-zero limit. This doesn't have that, but it still decays somewhat slowly compared to, for instance, in the disordered phase, in the non-symmetry broken phase here, this for Z2, this would decay exponentially quickly.
Yes, there's some like massless modes like somewhere.
Yeah, exactly. These Goldstone modes. So they where you sort of
Oh,
yeah.
we're in 2D. Good. Yeah, I see.
right. So this is related. I'm thinking about like positive temperature classical stuff for a second. So this is you can think about this as being related to the compact boson in one dimension. KT criticality. Mhm. So the commonality of these defects is you have a space G mod H of ground states. So I'm assuming the G acts transitively on the space of ground states, which generically will be true. If you have multiple orbits in the space of ground states, then you can find G symmetric perturbations that will favor one orbit over the other. Then codimension K defects correspond to elements of I K minus 1 of G mod H. Or if you have a defect, plot is like this line. There will be some K minus 1 sphere here. Linking it. Now, away from this defect, the system is approximately in one of these ground states.
Time dimension dependent.
Codimension K.
Sorry, yeah.
Yes. Yeah, so this is dimension, like whatever we want to call it, right? T minus. Yeah, it only depends on the codimension. So you have this K minus 1 sphere that we think of as, so here, G mod H is U1, right? So this is S1. We're thinking about winding around that S1. So this vortex is associated to pi 1. S1 and these domain walls are associated to 0 of S0, where you have C2 broken to nothing. So these are the defects that are interesting from the point of view of spontaneous symmetry breaking. But if you study explicit symmetry breaking, the story is a little bit different. So in spontaneous symmetry breaking, we had some space on which G acted transitively, which we could think of as specified by some kind of conjugacy class of stabilizer group of unbroken symmetries. But explicit symmetry breaking is defined by linear perturbation which by virtue of being linear, it naturally lives in a representation row of G. For example, when we did this perturbation of the EC2 breaking potential, X, the operator we're perturbing by, transforms sine rep of D2. So there's a different kind of defect that you would want to study associated to such a representation. So in general, to think about the change in potential or the change in the energy, however you want to think about it, as right. The X of epsilon A OA X. So thinking in field theory, it's like this, where this OAX is some kind of operator, for example, phi, which is an allowed perturbation of our theory, and these epsilons are some parameters that now carry some index for this representation growth. So for example, more interesting example in C2, we have ON. We can think about a generalization of this U1 breaking story. Where now we have a field phi, which takes values in the Rn. Here's a ON symmetry breaking model, spontaneous symmetry breaking. But then we can add to it perturbation epsilon, now transforming in the vector representation of ON.
Perturbation for every representation of the group, or do I need to pick special representations?
It's a good question. So in all the examples I know, if your group contains like a fundamental representation among your observables, so meaning that every element of the group acts non-trivially in the theory, then you can construct operators of any representation by just taking tensor products. I don't know if there's some weird rep theory loopholes that get you out of that in an interesting way, but yeah, I'm going to assume that there's perturbation operators for the transform in every representation. Okay, so we're going to define this row defect. by letting the epsilons depend on space. So if the dimension of rho is k, this is going to be a codimension k defect. And we're going to define it by writing epsilon a. We're going to write the coordinates. We're going to separate the coordinates into the normal coordinates, which I'll call y, and the parallel coordinates, which I'll call x. And what this is going to be is there's going to be some profile function, which is radially symmetric, so it only depends on the sum of the squares of the y's. And then there's going to be ya over absolute value of y. So this profile function, so it has to be 0 at 0 for this to make sense. There's different things you can choose. For instance, you could choose a linear profile that will be often easy to do calculations with, or you could choose a profile that grows and that has some kind of cutoff. But what we essentially want is that this function is 0 at 0 and then increases monotonically. And so what you can think of is that epsilon, similar to here, where the state we were in winds around a k-1 sphere, but in this ground state space, here our perturbation winds around a k-1 sphere. So I'll call S rho. So this is the sphere in the representation space. This is a natural defect to study because it's going to have a lot of symmetries. And so for the case of Z2, the ones that we've seen so far are rho defects. So for example, 2 and rho to be the sign rep, then you get essentially a domain wall. Now this is explicit symmetry breaking. So what you've done is kind of force the system to be in the plus state over here and the minus state over here. And there's going to be some domain wall. Well, it might not be exactly at x equals 0. It might fluctuate around a little bit. But you basically have isolated a single domain wall in studying this rho defect. Likewise, for U1, if you took the charge 1 representation, you would have a single vortex sitting at the center. But we could also take more complicated representations. For example, if we take 2 times the sign representation, this is going to be codimension 2 now. Now this is going to be a little bit stranger. It's going to look more like this. Plus minus in a kind of symmetric pinwheel configuration. So this is a very non-generic defect from the point of view of from the point of view of spontaneous symmetry breaking, but it's something that we can consider in explicit symmetry breaking. Non-generic because the sphere in this 2 times sign representation splits into a lot of orbits of Z2. Yes.
So in this case, this is still a codimension 1 defect, right? But then that the defect itself has intersections.
Right. So this defect, I mean, when I say codimension K, I'm being a little flippant here. So it might not exactly be codimension K. We're trying to make something that's codimension K. So the cases we'll be able to study are when it's actually good invention K, but in general, you'll have this other stuff.
Right, okay.
Yeah. Yeah, I'm not sure what I should call that dimension. All right. So we've seen how these domain walls sort of move around. They have a kind of dynamics associated with their motion. Now, what can happen is that there's, depending on the system we study, there could be other localized modes on the defect besides just their translational degrees of freedom. So I want to give you an example. There's this Rev 0 mode. So we study 1 + 1d two component fermions. Now we could do real or complex components because for spin 1, we have a nice real structure. We can choose our gamma matrices to be real. So this is Pauli X and Y. So if we do this, these are real matrices that satisfy the clip 1, algebra and exponentiate to some representation of spin 1. Now, the model we want to study we have the action or the Lagrangian. We have a kinetic term, and I want to think about adding to this kinetic term a mass term for psi. Now the rules for these, I wrote down some expression. The rules for these is that it has to be real. So you have to make sure that this is a Hermitian combination of all of the operators. And that's what forces you to have these i's here. So I'll leave that to an exercise to you. Now, the solutions, so there's equations of motion for this problem. Now it's a free problem in the sense of just being quadratic in size. So it actually, any body problem can just be solved by solving the equations of motion. And so to get the equations of motion, we do the usual thing with the Euler-Lagrange equation, and we find this. Dirac if we're talking about complex, or Majorana if we're talking about real. Now this has solutions. Psi has this spinor index transforming under spin 1. It has solutions which look like this. Where this energy is related to this momentum K by this relation. So these are the solutions. So if you plot this, the kind of hyperboloid, where the lowest energy state, so that's when k equals 0. The lowest energy state has energy m. So this system has what we call a mass gap. There's a lowest energy excitation above the ground state, which is to occupy that one fermionic state. So this property tells us that if we now consider our mass to depend on space, say like this, over in this region, we have a gapped system. Over in this region, we have a gapped system. So essentially, we have a localized theory. Anything left in this theory will be localized to x equals 0. So you can think about this. This is a row defect. Or say time reversal symmetry. So we have this anti-unitary symmetry. Down the 0 side, which takes mass. So this is going to be some kind of 0-dimensional. Zero-dimensional row defect. So if you thought about some system that had these fermions, where say time reversal was explicitly broken and coupled to this mass term, sorry, spontaneously broken, then you would have these domain walls floating around, and this row defect is just isolating one of them. The cool thing that happens, so let's actually take the linear profile. So this is not going to spoil what we just said. It's just going to get more and more gapped as you get away from the defect. Now the equation like this, and there's actually a time independent solution. Now time independent means it's going to have 0 energy. So we can just drop the time derivative here. So we have gamma 1 dx plus x times psi. So if we write, so if we write let me write u. So gamma 1, gamma 1 has eigenvalues plus or minus 1. So let me write the eigenvectors as u plus minus. And we notice that this has solutions. I plus minus is u plus minus. See that when you take the derivative of this profile function, it spits out an x. So if you have the sign right, which is going to depend on this eigenvalue of gamma 1, then you can get this to cancel. So notice that the plus sign is normalized. Normalizable. And the minus is not. -1 is behaving really badly, right? Whereas the plus, U plus, I mean, so that had minus up here, has this nice Gaussian profile. You can definitely normalize that. So what you get is a single zero energy mode. And depending on whether it's real or complex, and what we started with was real or complex, we get a real or a complex mode. So if we're in this real case, having a single Majorana, single real fermion mode is actually rather strange, because if you have a two-dimensional Fock space of a fermion, so a single complex mode, it decomposes into two real modes, the real and imaginary part. So this sort of has square root 2 dimension of its Hilbert state, which is somewhat anomalous, right? And the C case is also anomalous, but you have to add some symmetries to make it so. For example, if you take U1, then we direct C. This is also anomalous, because so here you have a fermionic mode, so it's a two-dimensional Fock space. Sorry, complex mode, so it's a two-dimensional Fock space. Now that mode itself has charge 1, so the difference in charges between those two states has to be 1. So if you have charge conjugation, they have to be plus or minus a half. That's the only way you can have charge conjugation. And that's a projective representation of this U1 semidirect C. So let me mention I have more time to do these calculations, but they're very slow on the board. I'll give you 2 exercises. So very similar calculations to this. So here's an exercise. So do the same thing, and now 2 plus 1 dimension. So you still have 2 component, and let's do 2 component real, and choose as our next gamma matrix this Pauli Z. It's also a real matrix. So now we get a real rep of spin 2, 1. And now show that I. So we're going to have a T, an X1, and a Y2 following our convention for the row defect. If we write this as f of X1 by I of Y2, then we can choose. So this is sort of separation of variables. We can choose this profile such that I satisfies a massless Dirac equation. So it's real. It solves this kind of equation with mass being 0. So it only depends. This will localize it to x1 equals 0. That's where this function will be peaked. So you have really a massless fermion on the domain wall, and Moreover, I is actually chiral. So it has a particular eigenvalue for. Yeah, so actually you only get one real component, which is associated with a normalizable F. So you have a chiral mode on this domain wall. That's pretty interesting. So you have mass less than 0, mass greater than 0, so 2 space dimensions. And you get a single massless chiral mode on the wall. Another good exercise. So 3 plus 1D. Okay. 2-component complex. Well, fermions. So these have a Majorana mass. They have 2 mass terms. So there's a psi bar psi term, and there's a I psi bar. You have a 5 psi. And if you form, so this is a 2-dimensional space. If you form the vortex in these, so you choose this to be r cos theta plus r sine theta in your 2 coordinates. Or actually, maybe it's, or shouldn't do that. So I should call this like x1 and x2. So this is like a row defect for the U1 symmetry of these Weyl fermions that this mass term violates. Then along this vortex, line, right? So this is going to be, it's going to have some codimension 2 solution. There's also a real so these are some calculations you can do with free fermions that are fun. Well, depending on your taste of gamma matrices, you might consider them fun or tear jerking. But we'd like to know, and what we'll explore in the other lectures is how stable are these sorts of conclusions to adding interactions to these systems. So for these free fermion models, there's been for a long time a mathematical formulation of them, this Galileo's index theorem. A nice place to learn about is in the appendix of the Seiberg-Witten paper on gap boundaries of topological orders from weak coupling. Anyway, so that tells you if you have some kind of mass matrix that depends on space in an interesting way. What's the structure of 0 modes at the origin? Given by some kind of winding numbers. But we want to ask, like, okay, what about interacting systems? And we want to phrase it in terms of anomalies. So we want to relate to this system, for instance, it has a parity anomaly. So this is also a time reversal breaking perturbation when we add the mass to 2 plus 1d. This 1 plus 1d1 also has a parity anomaly for this t breaking. And the U1 symmetry that's broken here also has an anomaly. And we want to know how that anomaly is related to these defect modes that we found on the row defect. But they're also anomalous. For instance, here we have some chiral fermion that has a kind of gravitational anomaly. Previously, we saw Majorana 0 mode that also has a kind of gravitational anomaly, or the complex 0 mode that has carries a projective representation, the global symmetry. That's my hour, right? That's a good time. So, thank you.
Coffee break. If there is any. Yes.
I'm slightly confused what these row defects are defects between, in the MX equals X. Are they like? X between row and X series? Well, it doesn't seem like there's a theory on the left and on the right.
So a defect, yeah, I just mean something that is like it's like a particular point that's distinguished. So for instance, the center. Well, the codimension K subspace where all of the X coordinates are 0 is a distinguished subspace because that's where the perturbation is turned off. Everywhere else, you've broken the symmetry in a sort of symmetric way where if you perform the symmetry, it kind of acts by just rotating this profile around. So yeah, defects. I mean, in physics, people use defects to just mean sort of like any kind of object that is like stationary. So here I'm adding it. It's like I've modified my problem in a way that's going to be true for all time.
But that's like a defect between two theories or a defect in a theory.
So if it's codimension 1, then you can think of like a domain wall. You can certainly think of as a defect between the two sides. Right. But if you have a vortex, say codimension 2, I don't know how to say it's a defect between something. Maybe you want to think of it as like a two-morphism rather. But you know, these things are not going to be topological generally. So I'm hesitant to use any sort of categorical language to describe them. But yeah, these are interesting because you know, here it's like you go from this thing to the other thing. But here, what's interesting is that you wind around it, right? The order parameter winds around the vortex. That helps. Okay.